Okay, so we're very happy to have Joel Hamkins from Notre Dame, formerly from CUNY, and formerly also in between at Oxford for a little bit, here to talk to us about pointwise, definable, and Leibnizian extensions of models of arithmetic and set theory. So thanks, Joel, for coming.
Yeah, well, thank you very much. It's a pleasure to be at MOPA, and I'm really glad that we finally worked out a time for me to come and speak at MOPA. So it's always a pleasure to see all of my New Yorker friends and everyone else here. Okay, so this is in part joint work with several people, including Hugh Wooden, Cameron Williams, Victoria Gitman, and also some of my own solo work. It's a big mix of different results. Okay, I'm going to start by just reminding us all what it means to be pointwise definable. So a model or structure of some kind is pointwise definable if every individual is definable without parameters. So every individual has a property that only it has in the model. And I really like this concept, and it's related to something that I've often talked about, which I call the math T argument, which is an argument I've heard many times at sort of the philosophical discussions that might take place at a math T, which is why maybe it's not such a good name, except I did happen to hear this argument a large number of times at various math Ts in Berkeley and so on and elsewhere. And so that's why it always reminds me of those great math Ts. But the argument is there must be some real numbers that we can neither describe nor define because there are uncountably many real numbers, but only countably many definitions. And this argument is often made, and mathematicians stand around and they nod their heads and say, yeah, that seems totally right. But actually, if you think more deeply about it, you begin to realize that it's problematic in many respects. And I've written a lot about this, but I just wanted to mention it today a little bit. So, of course, one difficulty with the argument is that it's not clear that we can define the notion of being definable as an internal notion. And furthermore, the existence of pointwise definable models, particularly pointwise definable models, say, of ZFC, pose a problem for the argument and shows that there can't be any kind of ordinary understanding of the math T argument in the sense that it could be formalized in ZFC, because there are pointwise definable models of ZFC. And in such models, the conclusion of the math T argument is not true. Every object in such a model is, in fact, definable. Okay. Let's leave aside the remarks that my son made a number of years ago when I first started thinking about the math T argument. And I told him, I was thinking about whether you could define every number or describe every number. And he said, I can describe every number. Let me show you. You tell me a number and I'll tell you a description, which is a remarkably successful strategy for refuting it. Okay, so a closely related concept to my way of thinking is the notion of a Leibnizian model. A model is Leibnizian if distinct elements have different properties. In other words, if you take any two distinct individuals in the model, then there's some formula in the language of the structure so that A fulfills the property and B does not fulfill the property. So any 2 points, you can tell them apart. So another way to say that is that any two distinct individuals have different one types in the language of the structure. And it's an interesting puzzle to think about the connection between pointwise definability and Leibnizian. Obviously, every pointwise definable model is Leibnizian. And the converse is an interesting puzzle to find, say, the challenge exercise. I mean, I know the answer, I know a pretty good answer, but I challenge all of you to think about producing a Leibnizian structure in a finite language with no definable elements. So Leibnizian structure, finite language, no definable elements. That's a kind of puzzle that is fun to think about. Okay, so they're called Leibnizian because, of course, these are exactly the models that fulfill Leibniz's principle on the identity of indiscernibles. Namely, this is just the contrapositive of the way I defined it up there. Saying that indiscernible individuals are identical is just the contrapositive of saying that if two individuals are different, then they're discernible. Then one of them has a property the other one doesn't have. Okay. Now I have a number of theorems, 4 goal theorems that I want to prove to you today. And the first one is a flexible new proof of this theorem. Every countable model of PA has a pointwise definable end extension. And when I told this theorem to Roman, Kosik, and Ali Enayat and Victoria Gitman a few months ago, Roman pointed out, well, actually, you can prove this using completely classical methods. And so I'm not going to tell you about that classical proof. I'm going to tell you about my new proof, which is very flexible, and I like it a lot, and I hope that you like that proof. And it works in set theory also. Every countable model of ZF has a pointwise definable end extension. In fact, we knew that already, just that first sentence, because we can produce, in fact, forcing extensions that are pointwise definable. But in this proof, we can achieve V equal L in the extension, which is like the barwise end extension property. So we're going to have a combined barwise extension property with pointwise definability. In fact, we can make any other theory true in the extension as long as there's an inner model of that theory that includes V equal Hod. Okay, if it's pointwise definable, of course, it must think V equals Hod because you don't even need the ordinal parameters. Okay, so those are the first two theorems. Countable models have pointwise definable extensions in arithmetic and in set theory. It has to be countable, of course, because there's only countably many definitions, and that's just basically the surviving content of the math T argument. But in the case of Leibnizian models, then, of course, a Leibnizian model, individuals are distinguished by their one type, and there's conceivably continuum many one types. So you could imagine, for example, Leibnizian models of size continuum. For example, the ordered real field is Leibnizian because any two real numbers have a rational number between them. And therefore one of the numbers has the property of being bigger than that rational number, and the other one does not have that property, and so therefore any two distinct real numbers can be separated. Okay, Leibnizian models can have size up to continuum, and the theorem is that every model of PA of size at most continuum has a Leibnizian extension. And similarly in set theory, every model of ZF of size at most continuum has a Leibnizian extension to a model of V equal L. And once again, we can get any theory in the extension, provided that it's true in some inner model and contains V equal Hod. So those are the four theorems I want to prove. And they all have at their core the same idea. And that idea is, well, it's flexible and soft, and I hope to convince you of this. It's using the universal algorithm, which is a theorem that goes back to Hugh Woodin. And Woodin's theorem says that there's a Turing machine program E that has this amazing universal extension property. First of all, if we think of the program as running forever, and periodically it might put a number onto the output tape of the Turing machine, but it's only going to do that with finitely many numbers. It's only going to spit out finitely many numbers. And PA proves that. Okay. And in any model of PA, then the program is giving us some finite sequence S. So in the blue model, it's giving us some sequence S. Then for any desired finite extension T in that model, it might be non-symmetric. Then there's an end extension N of the model in which, if we run the program, it will compute T. So if we wanted, maybe it gave us 10 numbers and we said, well, I really wish the number 17 came next. Then there's an end extension in which exactly the number 17 is the next number on the sequence. This is the universal extension property. You can make it do whatever you want if you run the program in the right universe, is how I think about it. Okay, it's quite remarkable. Okay, so the history, Woodin proved it initially for countable models, and then Blanc and Enayat. Blanc was Ali's PhD student at the time, and in his dissertation and in joint work, they proved it for all models, not just countable models. And I found a simple proof in 2017. And let me just describe to you a little bit about the proof, because it's quite nice. It's the algorithm is the petulant child algorithm. And in the first sort of process, what it does is I'm gonna define the program E. And what it does is program E embarks on a search for a proof that program E does not behave in accordance with a certain finite lookup table of input-output pairs. So let me say it again. Program E searches for a proof that program E does not obey a certain finite input-output pattern. And if it finds such a proof, then it does it anyway. Okay, so it searches for a proof that it doesn't have the certain finite behavior, and when it finds the proof, it computes in accordance with that forbidden behavior. So it's a petulant child because, like, it's told it's not supposed to do something, and then the first thing it does is do that thing right away. Okay, that's the first stage of the algorithm, but the point is that you can't prove that that program does not have a certain behavior, because if you could prove that it didn't have a certain finite behavior, then it would, because it would find that proof. I mean, for the smallest proof of such a form, it would have that behavior, which is a contradiction. So therefore, you cannot refute any particular finite behavior for this program. And therefore, it's consistent with PA that it does have that behavior, because you can't refute it. If you can't refute something, it means it's consistent that it's true. And so this is the idea that gives you the extensions. Okay, that's only the one-step extension, but of course the universal extension property allowed for sort of iterating this in every model. You can find it no matter what it was doing currently. And that's easily achieved by just doing the process in stages. So that what I just described is the first stage. But then at the next stage, we look for another proof, a better proof that it doesn't have a certain behavior that agrees with what it did so far. And I mean a better proof in the sense that it uses strictly fewer of the PA axioms, a strictly shorter initial segment of the PA axioms. And then when it finds such a proof, it does it right away. And then it looks for a still better proof and so on. And so PA proves that whole thing can happen only finitely many times, because the axioms are going down, and that can happen only finitely many times. And you can prove that if it does find such a proof, it must always be at a non-standard stage. And so we're always going to get the extension property because of this petulant child consistency proof that you can't refute anything. So therefore, it's consistent that it does, and so on. Okay, that's the universal algorithm. And let me mention that one can generalize it to higher complexity. Namely, if we want, say, sigma m elementary end extensions, not just end extension, but an elementary end extension, a partially elementary end extension, then we can find a program, a sigma m plus 1 definable finite sequence. Basically, you use the mth jump as an oracle, and you do exactly the same thing, but it's an oracle computation now. And so the complexity goes up to one more than the elementarity that you want. Okay, it's basically the same argument, though, but with an oracle. Okay, so again, every model can realize any desired extension T. In M, it gave us S, but we wish that it was going to give us T after that. And then there is an elementary end extension, a sigma M elementary end extension, in which the sequence computed is exactly T. Okay, but its sigma M truth is preserved because it's an elementary, a partially elementary end extension. Okay, so now let me prove the main theorem 1, that goal theorem, namely every countable model of PA has a pointwise definable end extension satisfying PA. And what I'm going to do is just build a tower of progressively elementary extensions using that sigma M definition. So first I start with any countable M0 that I want. And I can put any individual I want as the last element of the sigma 1 definable sequence, the CE sequence. I can make the last element of that sequence whatever I want, because I can just put it on next by the extension property. Okay, and then for the next stage, I look at the sigma 2 definable sequence, which has the universal extension property with respect to sigma 1 elementary end extensions. And I can put whatever I want as the last element of that sequence. But notice that because this extension is sigma 1 elementary, it preserves the earlier sequence. It's not going to add any new elements to the original sequence, because that would be sigma 1. And this is sigma 1 elementary. So because the tower is progressively elementary, whenever I put something as the last element of a sequence of that complexity, then the rest of the tower isn't changing that fact. So I'm making A0 definable in M1, and it's going to stay defined as the last element of the universal sequence in all of the further models. And similarly, I just do the same thing at each stage. A sub n becomes definable, becomes sigma n plus 1 definable, and that definition is preserved through the rest of the tower. The limit model is a model of PA because it's progressively elementary. These are all PA models, and they're becoming... Yes, was there a question? Feel free to ask a question.
הנה, את זוכרת אותו. שערות לבנות כבר, מעורבב.
Is that a question? Oh. Okay, so let's continue. So the limit is a model of PA because it's progressively elementary. So, and now the point is that, look, these elements I was making definable can be whatever I want. And so I can just organize the construction. I had a countable model, countable extension, and so on. There's only countably many points altogether here. And so I can just make sure that every point I added is at some point made definable. This is what I meant by flexible. This is a totally flexible argument because I can make whatever points I want definable in whatever order I want. And in the union, all the points are going to be definable if I arrange things properly. And so I've got a pointwise definable end extension. Okay, so, I want to just mention, actually, I could have started with sigma 6 elementary and then sigma 7 and so on. So I get a version of the theorem with sigma m elementary for any m I want. I can make a pointwise definable sigma m elementary end extension by just starting the progressively elementary tower, a bit further on. Okay, so now let me talk about the set theoretic analog of this. By the way, I'm totally happy to take any questions, so I think there's going to be plenty of time. Right. So when I first heard of the universal algorithm for PA models, I immediately wanted to prove the set theoretic analog, and I saw it Wooden at Newman.
May I ask a question?
Sure, please.
Oh yeah, so there's something I maybe don't understand this statement, or I was watching for this. So you're starting with an arbitrary countable model that might not be pointwise definable, right?
Right, yeah.
So somehow in this process, all these elements that aren't definable, somehow the ones that you had to begin with,
Yeah, the definitions
somehow
become
require
definable.
definitions by virtue. They
become
definable somehow
by being the last element on the universal sequence of that complexity. So A0, I put it as the next element on the definable sequence, and I never make that sequence any longer. So it's going to continue to be the last element on the sequence. This definition is going to continue to work all the way through because of the elementarity. And similarly, A1 becomes definable as the last element on the sigma 2 definable sequence in M2, and it's going to continue to be the last element on that sequence because of the elementarity. The sequence isn't getting any more.
I mean, at some point you work your way through all of the original elements, right? And then you process them.
Well, you have to interleave the new elements in with the old in order to handle them all.
Yeah. Okay.
Yeah.
Okay, thanks.
Okay. Yeah, I think that this is really the core of the argument, this idea of making things. Sure, go ahead, Hein.
What is pointwise definable?
Pointwise definable means every individual is definable without parameters.
Okay, thank you.
Okay, so let's right. So Wooden and I proved the set theoretic version of the universal algorithm theorem, namely for any countable model of ZFC M, well, there's a sigma 2 definable finite sequence of sets. So in ZFC, we're defining it, well, ZF actually, with the property that ZFC proves it's finite, and if M is any countable model of ZFC in which the defined sequence is S, then for any finite extension T that I want, whatever I would want to come next on that sequence, I can find a top extension And top extension means all the new elements are at rank higher than the old sets. In which, if I run the definition, I get exactly T. So this is the universal extension property. I can define a finite sequence so that it's ZFC proves it's always finite. And in any countable model, no matter what it is, then no matter what I wish I had after that, I can find an end extension where, in fact, I do have that. Okay, so it's the set theoretic analog, the ZFC analog of the universal algorithm. Okay, so this definition is somewhat more complex than the petulant child algorithm earlier, and it's involving forcing and descriptive set theory and so on. But at the heart of it really is the petulant child idea. We can't look for proofs anymore because in set theory, just because you can interpret a model doesn't mean it's going to be an end extension. The situation with ZFC is different from PA in that respect, that if I take the Henkin model of a consistent theory, I'm not going to get an end extension of my set theoretic model. So instead, I need to be more sophisticated and look for some rank initial segment V alpha of the universe, so that in the extension in which that V alpha is countable, in the forcing extension in which that V alpha has become countable, there is no top extension of that V alpha realizing that the very same definition defines the new set. So that's like saying that you're looking for a proof that you don't have a certain behavior. I look for a V alpha such that if I were to collapse that V alpha to become countable, then in that forcing extension, there wouldn't be a top extension realizing a certain finite behavior. And if I find such a V alpha, then I put that on as the next sequence. Okay, I'm glossing over some details there, but at its heart, it's the petulant child idea, but it's more complicated. Okay, so Cameron Williams and I were able to generalize this to the sigma 1 case. So with Wooden, the algorithm was, the definition was sigma 2, and it was producing top extensions, which seemed like the right thing to do. But Cameron Williams and I provided a sigma 1 definable finite sequence that has the universal extension property for end extension. So now the larger model won't necessarily be a top extension, because there's a hidden extra quantifier if you insist on top extensions. But if we only have sigma 1, then we have to be sometimes adding subsets of sets that we had and so on. But we still get this universal property. If a sequence is, if we have a countable model of CFC in which the sequence is S, then no matter for any finite T extending it, whatever it is, then I can find an end extension in which when I run the definition, I get exactly T. And then more recently, that's right. So we get actually, it's not just any end extension. We can get the theory of N to agree with any theory that's true in some inner model of M. So it's this kind of resurrection thing that happens. So in particular, it implies Barwise theorem about end extensions of V equal L, because that's one of, this might be CFC plus V equal L, and that's one of the cases that we would get. But if M has a measurable cardinal or something, then we can get an end extension where you think V equals L mu and so on, the large cardinal inner model theory. Okay. Now, more recently, I was able to get the sigma M version of this theorem, where the extension is sigma M elementary. So there's a sigma M plus 1 definable finite sequence of ordinals. Now, we're not going to get all sets, but just ordinals, and I'll explain why it has to be like that, with the universal extension property. Namely, if I have a model M in which the sequence is S, then for any finite extension T, I can find a sigma M elementary end extension in which the sequence defined is exactly T. Okay, and now the reason why you can't get it for all sets instead of just ordinals is precisely because you can use this trick in the way that we did for the PA models to produce pointwise definable extensions, and those extensions will have to have V equal Hod. And so if the original model did not have V equal Hod, then you can't find a sigma M elementary end extension that thinks V equal Hod, because that's a sigma, what is it, sigma 2, sigma 3? No, to v equal hot, it's a pi 2 statement, because no, pi 3, let's see, I have to think about it, but it's very low level complexity, the axiom v equal hot. I mean, you have to say for every set there's a v alpha in which it's defined. Okay. So let's prove the theorem, though. Every countable model of ZF has a pointwise definable end extension. And furthermore, we can get one satisfying v equal L. Okay, so this is how it goes. Okay, this somewhat more general version. Every countable model of ZF that has an inner model of this ZF of a CE theory ZFC bar, as long as it includes v equal hot, then it's going to have a pointwise definable end extension satisfying that inner model theory. So this is this resurrection property that I mentioned, namely, any theory that's true in some inner model, this ZFC bar, can become true again in an end extension, and furthermore, even a pointwise definable end extension. Okay, that's what the method is going to give us. So let's do it. In fact, we can at the same time get a sigma m elementary pointwise definable extension. And it's just the same idea as before, this flexible tower, the progressively elementary tower. Namely, you start with some countable m, and you pick any point you want, a0, and you make it the last element of the sigma 1 definable universal sequence. Okay, and now on the next stage, you're going to have a sigma 1 elementary extension, and so it's going to preserve that earlier definition because it's not going to make the sigma 1 definable sequence any longer. And we can put any a1 that we want and make it the last element, because we can find an extension in which any particular thing is the next thing on the sigma 2 definable sequence, and so on. So we make all these A1, A2, A3, and so on, we make them definable in the corresponding model, and that definition will be preserved to the later models precisely because of the increasing elementarity of the tower. And the limit model, oh, I'm sorry, this says PA, but it should say CFC here. I'm sorry. It's because I copied this earlier. So this, I'm talking about set theory models here, but the proof is exactly like the PA case. So this is a copy paste error. I apologize.
Joel, but it would be actually a fantastic theorem.
Right. This is not true. It's not a PA model. It's a CF model. In fact, it's a CF bar model. Okay, we can arrange that using the fact that we can get the inner model theory true in M1. Yeah, Chaim, you have a question?
No, technical remark. I mean, your
Sure.
voice doesn't sound clear. I don't know if it's my Wi-Fi or
Oh, I see.
your phone. It's something. Sometimes it sounds blurred.
Oh, I see. Let me make sure I'm on the right microphone. Let's see.
It sounds good here. I
Yeah.
detect a bit of a British accent.
A different microphone now. Is that better?
I think it was fine as is. I think it might be an issue on Chaim's end.
Okay, so I'm gonna stick with that other.
Joel, could I ask you again about that interleaving?
Sure, go ahead.
I'm just curious. I mean, is there? So you've got your original, you've got the elements of the original model, and many of which aren't definable, and eventually they, plus everything that you add, become definable. Right. So as you're doing this, right? I mean, you've got these stages, right? Now, I take it that even the original model is not exhausted until you go all the way through. Is that true?
Right, exactly. Because at any stage, you've made only finitely many of them definable, but there's only countably.
Oh, of course. Oh, of course, I'm being
together.
stupid. That's right. Okay. All right. So, but then you have to dovetail in all of the new ones. Somehow.
For example, maybe at every even stage, we code an element of the ground model. And then at every other stage,
Right.
we code the M1 sets. And at every other stage, we code the M2 sets.
Right.
Right. That's what I meant by interleaving.
Yeah.
I mean, we're just using a pairing function. So at stage K, interpret it as a pair, which tells you which model to look at and which element from that model is another way to do it.
Mhm. Okay.
Okay.
So I'm not understanding why this is sigma m elementary.
Oh, we have to just start. I'm sorry, this picture.
Oh,
if we
okay.
Yeah.
I see. So you
this slide is not the best slide. I'm sorry.
so just add m everywhere. So
just add m everywhere.
Okay, yeah. So start with sigma m, sigma m definable sigma.
If we
Sigma m
start with
plus
sigma 6 elementary and then sigma 7 and then sigma 8, and then altogether it's going to be a sigma 6 elementary extension.
Okay.
But we can do that for any m.
Okay.
Okay, so right. Okay, so to kind of summarize what we've got so far, and the universal finite sequence, the universal algorithm argument shows that anything you want can become definable using this definition. The last element on the universal sequence is a definition of an object, and it can define whatever you want. Because of the universal extension property, you can put any element as the next and last element on the sequence, and that's a universal definition that can be used to define whatever you want. And then in the higher arity, in the higher complexity, we can make anything we want as the sigma 2 as the last element of the sigma 2 sequence and so on with a sigma 1 elementary extension. Okay, so we get pointwise definability just by iterating that. We make something definable and then we make in a way that preserves the earlier definition, and then something else definable in a way that preserves the earlier definitions. And if you just iterate that, you can make it pointwise definable if you want, if you organize everything properly in the way that I was just discussing with, I think that was Adam, but I'm not quite sure because I don't see him. So, okay.
Yes, it was me.
Okay, great. So another observation to make is that pointwise definability is therefore what I call a switch in the potentialist system of models of arithmetic or set theory. Namely, if we think about the collection of all models of PA as a Kripke model, where a model has access to its end extensions, then we can turn pointwise definability on or off. We can go to an extension where it is pointwise definable if we're just in the countable models case, and we can go to an elementary end extension, which is therefore clearly not pointwise definable. So we can turn it on and off, and that's what it means to be a switch in the modal logic of that potentialist system. So being pointwise definable is something that you can turn on and off by going to end extensions. It also follows, because of the sigma m elementary nature, that there can't be no countable model of PA satisfies a maximal sigma m theory, because these are elementary extensions. Because we're adding new sigma m facts by extending the sequence longer. Okay, so right. And it also follows that the modal logic of this end extensional potentialism is exactly S4 for reasons that I've explained when I've talked about the potentialist system. So the basic picture is that the universal sequence, if you start in a model M, then you can extend one way by putting, say, a certain thing as the first element on the universal sequence, or you can extend a different way by putting something else as the first element on the sequence. And there's not going to be any way to combine those two extensions, because one of them thinks the number 6 is the first thing on the sequence, and the other one thinks the number 7 is the first thing on the sequence. And any common extension would have to agree on those facts. So what you get is this kind of tree development that's expressible directly in terms of the universal finite sequence itself. And from that, you can prove that the modal logic is exactly S4, because you can simulate all of these tree Kripke models. Okay, so let's now go to the Leibnizian case. I think I have time. So the goal is to do the same kind of analysis, but for Leibnizian extensions in place of pointwise definable. So remember, pointwise definable means every individual is definable. Every individual has a property that only it has. And Leibnizian means any two individuals are discernible, meaning that one of them satisfies phi of A and the other one satisfies not phi of B. So any two elements have a property that holds of one of them, but not the other. Okay. So, right. Now, it's easy to see that pointwise definable models in a finite language have to be countable. That's the math T argument that we discussed. Namely, there's only countably many definitions, so pointwise definable models have to be countable. But Leibnizian models could seem to have size at most continuum, because in a Leibnizian model, every individual is determined by its one type, by the set of all the formulas that are true of it. And there's continuum many one types in a finite language, or in a countable language. Okay, so it's a very natural question. Does every model of arithmetic of size continuum have a Leibnizian extension? This is the natural analog of the pointwise definability and extension results from earlier. Okay, and the answer is yes, so let me prove that. Okay. So the claim is every model of PA of size at most continuum has a Leibnizian extension, and in particular, for any M, we can find a sigma M elementary Leibnizian extension. So this is the proof strategy. What we're going to do is something like what we did before. Now, we're going to build a tower, and on the even stages, it's going to be fully elementary. And on the odd stages, it's going to be increased progressively elementary, but not fully. Okay. But therefore, if these are all PA models, because it is progressively elementary, the union model will be a PA model. And furthermore, it'll be a sigma M elementary extension, because they're all at least sigma M. Okay. At the even stages, it's, as I said, a fully elementary extension. And what we're going to do is create, so these are models of size continuum. We're going to create a countable set of parameters which are able to discern, over which we can discern all the prior elements. Okay. So every model of size continuum, I claim, has an elementary extension with countably many new points, such that if I have constants for those points, I can discern everybody that I had before. Okay, but of course I'm adding a lot of new elements. Okay, and at the odd stages, I'm going to make those countably many new points that I added definable using the universal algorithm idea. So I'm adding countably many new points. I mean, I'm adding continuum many new points at each stage, but countably many of them I'm thinking of as fixed. Those countably many new points at the fully elementary stages are going to support the discerning of the earlier elements. And then I'm going to make those countably many points definable using the previous pointwise definable argument. Okay, so let me explain again. There's these two kinds of steps. At the even stages, we create discernibility relative to countably many new constants. And this is just a compactness argument. So if M has size continuum, I'm going to associate with each individual a binary sequence, S sub A. Okay. And now I'm going to write down this theory, which is the elementary diagram of M, including constants for every element of M, together with infinitely many new constants, C sub n. And I'm going to say that C sub n codes a set with A as a member if the sequence that I associated with A has a 1 in that bit. Okay, so different elements have different sequences, and therefore there will be some n such that A is going to be an element of C sub n and B is not going to be an element of C sub n, right? So this is how I'm going to discern them. C sub n is going to discern its elements from the other individuals that had a different bit in that coordinate n. Okay, so this is a finitely consistent theory, because if I have only finitely many of these assertions, then I can interpret these new constants. If I only have to satisfy finitely many of these coding requirements, I can do it inside M, and that's going to satisfy the diagram. So it's finitely consistent and therefore consistent And so I can get a model of this theory, which is going to be an elementary extension because I have the diagram here. And it has these countably many new elements, Cn, and those elements discern all the elements of the original model. Because as I said, any two distinct elements of M have different binary sequences associated with them, and they disagree on some digit n. And one of them is coded into Cn and the other one isn't. And so therefore, they're going to be discerned relative to these constants C sub n. Okay. And then at the odd stages, we just make those accumulating constants definable. The whole thing is omega many stages, and at each of the even stages, I'm adding countably many new constants, and then at the odd stages, I'm doing the interleaving on those constants to make sure that they become successively definable. And I can do that using the increasingly complex universal definitions. Okay, so in that way, we have this progressively elementary tower in which the constants all become definable, and those constants support the discernibility of all the other elements. Any element in the union is showing up at some stage. It's discerned by constants added at the next even stage, and those constants are definable at some odd stage later on, and those definitions are preserved to the limit, and so the whole thing is Leibnizian. Okay, so that's a proof of the goal theorem 3. And I guess that's it. Oh, I see. I didn't have a slide for the set theory version. It goes just the same. This construction works just the same for PA as for ZFC. And so so that's it. Thank you very much.
Thank you, Joel. So let's all thank our speaker. And we can open up for questions from anyone. So go ahead. You can unmute yourself and just go ahead.
I have a quick question. It's Ken McAloon, the Invisible.
Oh, sure.
The petulant child, it's a kind of Rosser formula, yes?
It's something like that. I mean, there's another proof that uses Rosser's formulas explicitly, and that was my first argument for that result. But I wouldn't say the petulant child is directly like Rosser because, I mean, the algorithm is, let me just describe it again. The algorithm is program E looks for a proof that program E doesn't obey a certain finite table of input-output values.
Right.
When it finds such a proof, it immediately starts obeying that table.
But are any two petulant children equivalent? Is there anything known in that direction?
Oh, I see. That's an interesting question. Let's see. I think it's probably quite similar to the Gödel sentence kind of situation. I don't know the answer to that. Yeah, so you want to know, do all such ways of implementing that petulant child algorithm produce the same function, I guess, is the question, right?
Yeah.
And I don't know the answer. I haven't thought. That's an interesting question. Yeah, I don't know the answer to that.
Mm-hmm.
I mean, of course, there's a lot more one has to say about it because I've defined the program E by referring to program E, and so one needs to solve that self-reference. But this is just the CUNY recursion theorem. It's quite standard in computability theory. If you're defining a program, a Turing machine program, then you can make reference to the Gödel code of that program itself, and there's always going to be a solution of that self-reference. And that's exactly the content of the CUNY recursion theorem. It's something like the Gödel fixed point theorem, right? But for computability. And actually, in the set theoretic case, because in the set theoretic version of the theorem, let's see, where is it? Here. It's not a Turing machine program anymore, but we're defining a certain finite sequence in set theory. Then really what we're using is the Gödel-Carnap fixed point lemma to solve the same kind of recursion here, because the definition is making reference to the very same definition being run in some set model. So it's a very similar self-referential situation there.
So there's something, it's probably not related. It's just another instance of a fixed point theorem, but this description of the petulant child, that story, kind of reminded me in the proof. Why am I forgetting the? This is the identification of GL as provability logic, right? And there's this story about a traveler not having a passport and getting a transit visa, and it had a similar ring to it. But maybe all these stories
right.
do.
It's you can only enter the country. What is it called? It's the itinerant.
Yeah, I don't know a name for it, but it's
we mentioned this and we give the
you do.
citation in our paper. It's the wandering. Okay, so the rule is you can't enter the country unless you prove that you're going to leave the country,
which actually happens in
yeah,
practice.
Exactly. And so you can interpret this kind of rule as an algorithm, and it's remarkably similar in some ways to this petulant child algorithm. That's exactly right. So if you look at my paper on the universal algorithm and the arithmetic potentialism, we cite all that. Yeah.
Christian?
Is it a miracle that?
Hold on, Ken. There was a hand raised. Sorry.
Okay. Could I or not? I'm not sure. Probably I was the last person.
You can go, Christian.
Okay, thank you very much. Thank you very much, Professor Hamkins, for your very motivating and inspiring talk. I would like to say that your pointwise definability in the end extensions of ZF model is just what I need from the purely philosophical perspective, as a person interested in the logical and philosophical improvement of the model theoretic argument, especially his formal tissue of his argumentation. However, in this context, I would have one question. Do I understand correctly that you propose that the P1 in general PM definability or definable finite sequences? Am I right? Because of the nature of the proof of Putnam's theorem, I would like to ask you about the same possibility of considering definable finite sequences in end extensions for PM or P2 formulae, because Putnam in fact uses this type of formulae because he encodes his statement, his theorem as this P2 formula. Could you say me something about it? Maybe the problem is trivial. Maybe we can extrapolate your results for another type of arithmetical formulae, but maybe the problem is not trivial.
Oh, I see. I'm not quite sure I understand exactly what the question is, but the theorem that I was talking about is the claim that if you have a countable model of PA, then for any degree of elementarity you want, you can find a sigma m elementary end extension, which is pointwise definable. So you can preserve the current sigma m diagram fully and make everything else definable. So of course, those new definitions are going to have to generally be more than sigma m complexity, because if they didn't work before, they won't work now if it's sigma m elementary. So most of the definitions are going to be more complex than sigma m if you're achieving it in a sigma m elementary end extension. But I'm not exactly sure how this relates to Putnam's argument. I mean, except for the observation that we can settle the modal logic completely. The modal logic of end extensional potentialism is S4, exactly S4, nothing more than S4, precisely because of this universal algorithm. I mean, I think prior to this, to these methods about analyzing the modal logic of these extensions, it was very often stated, including in Putnam's paper, I think, where they just are quite sloppy, in my opinion, about what the modal logic is. They'll say, oh, S4, S4.2, S4.3, whatever. And there's no attempt made ever to give an upper bound. In other words, to find exactly what the modal logic is, but only the lower bounds. But the lower bounds are very easy, usually, to prove. And so the new part of this analysis is that we give upper bounds on the modal validities and achieve exactly S4. Nothing outside of S4 is valid in that concept of arithmetic potentialism, precisely because of the universal algorithm. You can build these trees, and then you can code finite Kripke models on those pre-tree structures, and that shows that you can't ever have something outside of S4 being valid. I'm not sure if that answers your question, though.
Okay, it's very interesting, but I'm not sure. I have a feeling that adopting the Kripke models as a semantic basis for further reconstruction of Putnam's argument, it will be a bit of challenge at least at this stage of my comprehension of the issue. But thank you for your recommendation.
So there's a
Mhm.
paper that I wrote with Oystein Linnebo about set-theoretic potentialism, where we explain there's a huge variety of concepts of potentialism, depending on what kind of extensions you want. For example, do you just allow forcing extensions, or do you allow just top extensions, or do you allow end extensions, which might be a mixture? And they all have different modal theories and so on. And so one response that one can make to the sort of potentialist set theory is that there isn't just one kind of potentialist set theory. There's like this huge spectrum, and they have different modal theories and different natures and so on. And so if one is going to talk about set theoretic potentialism, one should really sharpen the concepts and figure out what exactly is the nature of the potentialism one is talking about.
Okay, thank you very much.
Any connection with the quick question? Any connection with the Myhill's old paper in the Proceedings of the National Academy of Sciences on pointwise definable models of set theory?
I think he observed, right, that the minimal model, the Shepardson-Cohen model, is pointwise definable and so on. So I think is that right? Or
yes, and then you could have extended to the Gödel-Bernays model, and then you have a non-normal class which enumerates the universe.
Yeah, so those arguments are going in. Yeah, you're making pointwise definability by taking an inner model when you do those arguments. Whereas here we start in any model you want and we find an end extension. So it's much harder. It seems a much more difficult thing to achieve pointwise definability by, for example, if you take any model of CFC plus V equal Hod, then if you just take the definable elements, that's going to be an elementary substructure because the Skolem functions are definable. And I think this argument is probably in Myhill's paper. And so if you just keep the things that were definable, then that is an elementary substructure, and therefore that's a pointwise definable model because the definitions still work, right? And so you're throwing almost everything away when you do that. And so it's much harder to start in a model and then achieve pointwise definability in an outer model. And there's a paper that I wrote with, oh my God, who are my co-authors? David Linetsky and was it Jonas Reitz, I think, on pointwise definable models. And we started with any model of CFC and found a forcing extension which was pointwise definable. So that's an end. Forcing extensions are end extensions, and we did it with GBC also. So every countable GBC model, Gödel-Bernays model, has a forcing extension which is pointwise definable. So that's the beginning of making things definable by adding, yeah. And here in these cases, we're getting these end extensions, which are furthermore sigma m elementary, and which such that the extension is also a model of V equal L, which is the kind of thing Barwise was getting. And so it's basically a completely different situation to be growing outward instead of finding it by growing inward.
Joel, if I may now make a small comment.
Sure,
But
please. Yeah.
right there, because you alluded, you mentioned at the beginning those classical results from which the result about models of PA follows.
Yes.
And I have to say, I like your construction very much. It's all working beautifully and smoothly. But in the case of countable models of PA, there is this sort of the flip side. When you say, well, how much work does it take to get from a model that already has lots and lots of undefinable elements, like a very saturated models, and you construct this end extension when everything becomes definable. But looking from the other side, those pointwise definable models exist. Right? There are lots and lots of them, and there could be pointwise definable for different reasons. Well, and then the fact that some other model, the classical models were by embedding, like Friedman, like embedding theorems. Then now what it takes for any other model that may have lots and lots of undefinable elements to embed as an initial segment into one of those. So you need just two pieces of information, the standard system and its sigma 1 theory. And once you have both criteria satisfied, you embed one in the other. So it's sort of like a different vision. It's not really extending something, but embedding something in the.
I see.
In
I see
another
the perspective on the remarks that I just made, because
right,
you could sort of either throwing things away or as
right.
Interesting.
Right. But because in the other ways, you prove that you're using this universal algorithm. You prove essentially a kind of a version of Scott's theorem. You create using the algorithm. You simulate any standard system to begin with, because you make this end extension, the standard system of that extension.
I see. Doing the particular way
the coding, right. You're weaving in the coding, and you will reconstruct the standard system anyway. You will make it definable from those points. The theory of the model will reconstruct the standard system, and it's done through the algorithm.
Yeah, that's quite fascinating. So there's an open question here about, in the Leibnizian case. That's really great, Roman. Thank you so much. But I just want to mention this. In this construction, the odd stages. Let's see. The odd stages are end extensions, because this is the universal algorithm part of the argument. But the even stages, the compactness argument, we don't get end extensions there in order to achieve Leibnizian. But I don't know a priori why it might be impossible to do it with end extensions.
Because the standard system might be too small.
So at the even stages is the one where we have a model of size continuum, and we're finding an extension with countably many points that support the discernment of all the old elements. And it's this compactness argument, this one. And I just don't know how to do it in an end extensional manner, because I'm just taking the diagram and arguing with compactness. So it's open, as far as I know, to prove the theorem for Leibniz.
So Joel, I might be wrong, but I was listening to your proof. I thought that in the process of coding, discerning elements by adding those infinite sequences, you actually produce continue many elements. Now it has to be countable number. I think it seems like you're producing continue many types that have to be somehow coded in the standard system, but I might be wrong.
We only need countably many constants. There's continue many types, namely the bit patterns.
Right, but if they're of fixed complexity, that all those types will be coded in the standard system. So the standard system will have to be uncountable. So if you start with an uncountable model that has a countable standard system, you will not be able to do that.
End extension, then
it couldn't be an end extension.
Okay, I see. I see. You're saying that the sequences that are used must be in the standards. No.
The codes. The types of elements that code. I'm not quite sure. The types of those let's see.
I know that you can have a bad assignment of the sequences, which enables you, like, you definitely can't.
No, because you look at least at anyway, maybe it's something I may be wrong, but not just the types of the you have countably many of them, but combined with other elements. So then you have types of tuples, pairs. So maybe you have continue many types of pairs.
Right.
They are of fixed arithmetic complexity, and that will already beef up the standard system.
Right. Yeah. Okay. Well, this is a good strategy to think about. I guess one wants to refute it or something, right? I mean, to refute the claim that you can do it in end extensions is what your remarks are aimed at, right? Yeah, okay, yeah, that's a good suggestion.
Yeah, and I want to say another thing that about uncountable Leibnizian models. The first one to construct them was Julia Knight, and then she wondered about some extension of the result into doing things when you have the models when you do not have indiscernible finite sequences of given length. And this turned out to be harder and somehow related to some Ramsey properties of cardinals. So this is sort of something stronger than Leibnizian. The Leibnizian say you don't have sequences of length 2 that would be indiscernible. But how about not having sequences of length 3 or 4?
Oh, interesting.
Realizing the same time, and apparently there's some combinatorial problems with that. And there were some open problems left for models of PA.
Thank you very much.
Okay, other questions or comments?
I have a question. Sorry, so it's in if you're just taking an end extension of your model of set theory, you can get Barwise's results, right? That it's possible that V equals L holds in the end extension.
Yes.
Do you have anything similar if I mean obviously you can't get V equals L if you're taking a top extension. Did you settle on the complexity of V equals HOD? I mean, would it be possible that you could
Yeah, that's what I was claiming. So you can get any theory in the extension that's true in an inner model of V equal HOD. So for example, if there's large cardinals, then there's going to be inner models of V equal HOD that satisfy the inner model theory of large cardinals like V equal L mu or whatever. Then you can achieve that same theory in an end extension.
So this is when you're using your result with Cameron, right?
Yes, that's right.
So what about if you're using your result with Wooden?
Oh, I see.
Top
yeah, that's much harder. We don't get the inner model theory resurrection, let's see, in that case. But actually, the generalization, this one, does achieve it again, actually. But so a sigma M elementary, if M is at least 2, will be a top extension because the V alphas have a certain definition, and so of low complexity. And so once M, or maybe 1, let's see, if M is at least 2, I think it's enough to make these are top extensions. So in this generalization, and I can also achieve so of course it's still going to have V equal HOD in the extension because that's part of sigma M anyways. But I can also achieve any theory in the extension that's true in a sigma M elementary submodel, in a sigma M elementary inner model. So there's something like what you're saying is true. Definitely V equal HOD, we can do that.
Okay, cool. Yeah, thanks.
Oops.
Okay, other questions? Okay, let's thank Joel again. Thank you, Joel.
Thank you so much.
This is great. Yeah, I had something in my mind at one point, but Roman eventually answered it in his spiel that
He knows everything.
I wanted to ask if these sort of more classical methods could generally, but if it has to do with standard systems and theories, that's clearly not going to generalize past PA. So, but anyway, this is very fascinating.
But some of those things do work for ZF too, right? Some of those.
I mean, because in PA we use the fact that like things with that essentially everything is determined by the theory in the standard system. Is that still Is there an
Well,
analog?
there's
of that?
analogs of the Friedman
okay.
embedding theorem and set theory too, about getting
Oh.
models of set theory also being isomorphic to an initial segment of themselves and so
Oh,
on.
that's great. That's really interesting. Okay, no, that's fascinating. We will likely have one more talk this semester from Ali and Nayat, and we're still working out the date on that. It may be as early as next week, but still waiting to hear back. He's currently traveling right now, so we'll figure that out. So stay tuned. Keep an eye out on the emails.